Welcome. In this video, we'll dive deep into LeetCode problem number 704, binary search. This problem is a classic must-know for technical interviews, testing your grasp of searching algorithms and array manipulation. We'll thoroughly explain the problem, break down a step-by-step solution, analyze its complexity, discuss potential pitfalls and variations, and demonstrate both Python and Java implementations. By the end, you will have a strong understanding of binary search, its practical usage, and how to effectively solve similar problems in interviews. Let's go through the problem statement for LeetCode problem number 704. You are given a sorted integer array called nums and a target value. Your goal is to find the index of the target value in this array. If the value is present, return its index. Otherwise, return -1. Consider example 1. Nums is 1, 3, 5, 7, 9, 11, and the target is 5. Since arrays are indexed starting at 0, 5 is at index 2. So, we return 2. Example 2. Nums is -8, -3, 0, 2, 4, 10, target is -3. -3 resides at index 1, so we return 1. Example 3. Nums is 2, 5, 7, 14, 19, target is 6. 6 is not present in the array, so we return -1. Each example demonstrates different scenarios, finding the target, locating it at a negative index, and not finding it at all. Moving on, let's cover some important edge cases and constraints for LeetCode problem number 704. First, if the target is at the first index, such as 2 in, 2, 4, 6, 8, we return 0. If the target is at the last index, such as 8 in, 2, 4, 6, 8, we return 3. If the array is empty, any target should return -1, since no elements exist. When the array has just one element, if it's equal to target we return 0, otherwise -1. Finally, if the target is not in the array and is not present but would have fit between two values, we also return -1. The constraints are important. Arrays can be up to 10,000 elements, with values between -1 billion and 1 billion. The array is always sorted in ascending order, and all values are integers. These conditions are crucial when choosing an efficient algorithm. Let's discuss possible approaches for LeetCode problem number 704. The most straightforward way is a linear search, checking each element one by one until you find the target or reach the end. However, for an array with up to 10,000 elements, this can be slow, with a time complexity of O(n). Since the array is sorted, binary search is far more efficient, using a divide-and-conquer strategy. At each step, you examine the middle element. If it matches the target, you return its index. If the target is smaller, you only search the left half. If it's bigger, search the right half. You repeat this, having the search space at each step, until you find the target or run out of array. This achieves logarithmic time complexity, O, log n. The trade-off is that binary search only works if your array is sorted. In this case, since the input guarantees sorting, binary search is the optimal choice. Let's break down the algorithm for binary search, which is ideal for LeetCode problem number 704. Start by initializing two pointers, left at 0 and right at the last index of the array. We loop as long as left is less than or equal to right. Each iteration, calculate the midpoint using left plus, right left, divided by 2 to prevent overflow in languages with integer limits. If the number at mid matches the target, we return mid as the index. If the number at mid is less than the target, we move left up to mid +1, narrowing the search rightwards. If it's greater, we move right down to mid -1, narrowing leftwards. If no match is found, return -1. Key insights include always updating your pointers after comparisons to avoid infinite loops. Computing mid this way is a best practice in some languages to avoid overflow. Binary search's strength is having your search space with each step. Continuing with binary search, let's look at additional implementation details for LeetCode problem number 704. You can use either an iterative or recursive approach. Iterative is common in interviews and production code for simplicity and stack safety. Edge cases like empty arrays, single-element arrays, and targets at the array boundaries are automatically handled with the basic loop logic. The algorithm's time efficiency allows it to handle very large arrays, while the space efficiency means it can run on devices with limited memory. Here is the Python implementation for LeetCode problem number 704. We define a class solution with a method called search. We initialize left and right pointers, and as long as left is less than or equal to right, we find the midpoint. If the value at mid matches the target, we return mid. If it's less than the target, we shift left up, otherwise, we move right down. Once the loop ends, if no match is found, we return -1. This concise code encapsulates all core logic for binary search and handles all edge cases. I'll walk through the logic line by line to clarify each part. Going deeper into the Python code for LeetCode problem number 704, the function accepts two arguments, the array and the target. We set our left pointer to 0 and right to the array's last index. As long as the search space is valid, we use integer division to compute the midpoint. If the middle element matches the target, we return its index immediately. If the mid element is less than the target, then the target must be further right, so we move left up. Otherwise, it's further left, and we move right down. This three-way comparison directs the search efficiently. If the target is not present, we return -1. Here is the equivalent Java implementation for LeetCode problem number 704. The logic remains the same as in Python. We define a public method inside a class solution, accepting an integer array and target value. We use static typing for variables, left and right are integers. The loop checks if left is less than or equal to right, and mid uses integer division. The comparisons and updates to pointers follow the same rules. If no match is found by the loop's end, we return -1. Key differences from Python include variable types and semicolon usage, but the core logic stays the same. Let's walk step by step through two detailed examples for LeetCode problem number 704. First, for nums 2, 4, 6, 8, 10, and target 8. We start with left at 0 and right at 4. Calculate mid as 2. Nums 2 is 6, which is less than 8, so we update left to 3. Now, left is 3 and right is 4, mid is 3. Nums 3 is 8, equal to the target. We found the value and return its index, 3. Second, nums is -10, -1, 2, 3, 5, looking for -10. Left is 0, right is 4, mid is 2, value 2, which is greater than -10. We move right to 1. Now, left is 0, right is 1, mid is 0. Nums 0 is -10, a match, so we return 0. This demonstrates how binary search adapts for different targets and array contents. Here's another example. Suppose nums is 1, 4, 8, 12, 16, and target is 15. We start with left at 0, right at 4, mid at 2, value 8, which is less than 15, so left becomes 3. With left at 3 and right at 4, mid is 3, value 12, also less than 15, left becomes 4. Now, left and right are both 4, mid is 4, value 16, greater than 15, so right becomes 3. Left is now greater than right, we exit the loop and return -1. This shows how binary search effectively determines when a value does not exist in the array. Let's analyze the complexity of our solution for LeetCode problem number 704. Binary search halves the search space each step, so the maximum number of steps is the base 2 logarithm of n, the array size. For a 10,000 element array, this is only about 14 steps, so the time complexity is very efficient, O log n. Space complexity is minimal, as we only use a couple of pointer variables for left, right, and mid, no extra memory allocation for data structures. Thus, space complexity is O(1). Comparing to linear search, which would use O(n), time for scanning every element, binary search is clearly more efficient for large arrays. Both approaches use constant space. In summary, for LeetCode problem number 704, binary search is optimal when working with sorted arrays. If you encounter unsorted arrays, consider different strategies, such as using hash tables. When preparing for interviews, always pay attention to sorting guarantees in the problem description. The combination of efficient time and low space usage makes binary search an essential technique for both coding interviews and practical problems. Let's finish with common variations, mistakes, and practical tips for LeetCode problem number 704. The basic binary search may be extended to find the leftmost or rightmost occurrence of a target, which is important when the array contains duplicates. Other variants involve searching in rotated sorted arrays or finding the right insertion position if the target is absent. Mistakes often arise from incorrect pointer updates, errors in computing the midpoint, or neglecting edge cases. For interviews, practice both iterative and recursive implementations, watch for integer overflow, and always confirm whether the array is sorted. Interviewers may ask about more complex binary search scenarios, so be ready for follow-ups. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!